Okay, the recording should be starting now. Screen sharing will start. Let's just see. Okay, people confirming they can hear me. Okay, screen sharing starts now. And seems to be working. So let's just quickly, before I forget, that's the code for anyone watching this later, just so that I don't forget to do that. And then let's begin. So Mr. Satungu would have started off with the linked list with you. I think I'll just go back a little bit and just revise the basic idea again before continuing. He said he got up to 27 with you, but let's just recap and then we can continue. So basically what we're looking at here is data structures that aren't based on the data being next to each other in memory. So the key idea of an array is that data is contiguous. So contiguous means that they share a border with each other. So if you think of Africa, the contiguous African countries would be countries that are connected to each other by a shared border, or to another country with which they share a border by land, and then again and again and again. So South Africa and Egypt would be part of contiguous Africa, continentally speaking. But a country like Madagascar wouldn't be contiguous because it doesn't share a land border with the rest of Africa. So contiguous countries are next to each other directly, and arrays are exactly like that. An array works because every data point, every element in the array is next to each other element in the array. Technically speaking, and strictly speaking, the way we do multi-dimensional arrays, if you do a dynamic array, isn't contiguous, because each row will be contiguous because you allocate them in one block with new. So everything you allocate in one block with one new is guaranteed to sit next to each other in memory. But the way in which we do two-dimensional dynamic arrays with pointers to pointers, only each row will be allocated in a single new. So it's technically possible that one row will be well before or well after, or there'll be a gap between some of your rows and the rest of your two-dimensional array. And you'll never really know because you always access it via indexing, which is just pointer dereferencing in disguise. So that's fine. If you do a fixed length 2D array, it will definitely be one block of memory in the array, one block of memory. So if you remember, arrays in C++ are what they call row major order. So if we had a fixed length array that contained 1, 2, 3, 4, 5, 6, 7, 8, 9, oopsie, 8, 9 in memory, and it was fixed length, it would be converted into simply 1, 2, 3, 4, 5, 6, 7, 8, 9 in memory. Your array variable would store the pointer to the first element, and then C++ would handle the arithmetic of converting two indices into the equivalent one-dimensional array index. With double pointers or triple pointers or whatever, that obviously doesn't work. It's simply a one-dimensional index at each step, but there is still an expectation that within a row, so let's say if we had a dynamic array, it's possible our array could look like this. We don't know, we don't care. Doesn't matter because we get the pointer to our row and then we index into the row to get the value. So we are safe, but as long as each element in each row is contiguous, the scheme works. But it still relies on contiguous elements, at least at the row level, if not the entire array. So that's what we built all of our data management stuff that we've implemented ourselves with, is this notion of contiguous data. So linked lists free you from that. And they say, what if every data item was wherever it needed to be in memory? Can we build a data structure out of that? And the answer is yes, we can. They're called linked lists, but they're only the first kind of node-based data structure that you'll see. You'll spend quite a bit of time in Computer Science 3 studying more advanced node-based data structures, namely the various kinds of trees that exist and graphs. So this is a good segue into that. Linked lists are widely used, surprisingly enough, even though they have severe limitations. If you use them to access values in sequence, one after each other, they can be very efficient in terms of accessing one element, then the next one, then the next one. They're not as quick, they're much slower, in fact, at accessing elements that are out of order. So if you want to suddenly jump to an element that's in the middle of your linked list, you have to start at the beginning and traverse through your linked list till you get there. So non-sequential access is much slower. I mean, to be honest, like accessing arrays sequentially, if you're doing pointer arithmetic or if you're doing even indexing, that's still in the same order of complexity. So linked lists are as fast as arrays for sequential data in terms of broadly speaking. We'll discuss after the second semester test how to analyze and compare things like space and speed sort of more formally. And then for non-random access, they're much slower. So why would you want a linked list is a good question. Well, for one thing, some data is naturally representable as things that are linked together. Linking them as a single list has its disadvantages. But the fundamental data structure for some programming languages, particularly functional programming languages, so a language like Lisp, the Lisp processing language, which is still alive and well today, has its fundamental data structure a linked list. And many things like Haskell and ML use linked lists as their underlying data structure. Because of the way you program with them, it doesn't really matter so much that you don't do arbitrary indexing efficiently, because the style of programming steers you away from arbitrary indexing anyway. So that's one thing. The other thing is, think about an array in memory. Let's say we've got a fixed amount of space. Let's say we've only got that much memory. If we have this amount of data full in our array, and let's say it's not actually evenly spread out. Let's say we've got gaps like this, right? And we wanted to allocate space for a two-dimensional array that was the same size, that 3 columns and 1, 2, 3, 4 rows. There's enough space in memory to do that, but we might not be able to do that, particularly if it's fixed length, because there isn't a single run of data that's long enough to accommodate us. Whereas with linked lists, each data item is allocated on its own with its link, and so you can sort of thread yourself in between the non-contiguous data, the fragmented data we call it. The other alternative is to have something running in memory that moves everything about and defragments your memory, which you might get in a language where the memory is managed for you, like .NET or the Java virtual machine. Although, to be honest, I don't actually think they bother spending much time doing things like that anyway, but they could in principle. But any programming language where you have direct use of pointers can't work like that, because as soon as stuff gets moved, all those pointers are invalidated. So linked list is a way to use all of the memory if it's quite fragmented as well. So those are a couple of reasons why you might want to use a linked list. But the core of the linked list is that you've got the data item and a link leading to the next item. That creates the simplest form known as a singly linked list. You can, of course, have a link leading backwards as well, which then becomes a doubly linked list. And then, as you'll see in Computer Science 3A, if you relax the requirement that a successor or that a node that comes afterwards is an immediate successor, you'll basically have trees. And if you relax the requirement that no successor can also be a predecessor, you have a graph data structure. So what you see here can build up to be some of the more complicated data structures that get used in computer science. So what we always need to keep track of is the beginning of the linked list. In the same way as in an array, you always keep track of the pointer to the first element. You also keep track of the pointer to the first element in a linked list. We have a special name for that. We call that the head. And then the last element in the linked list will point to null if it's the last element. And we can sometimes add in an extra pointer which points directly to the end, which we call tail. Often. Sometimes it's first and last, but head and tail are very commonly used. So the important thing to do is to keep track of the difference between the memory addresses for the links and the values that are stored inside the data item itself. So at memory address 1200, you will find the first data item. So head is just a pointer. It doesn't contain any value, but you follow it and you get to the node, which contains the value you want, as well as a link to the next one, 1575 in that case. So this is the key. You will be implementing that data structure or that structure a lot in exams style questions and any practical you do on it. We typically will do it in a templated style because you don't just want a container of integers. So we will typically have something along the lines of struct type name t, and then not struct, sorry, template type name t, and then struct, which we will typically call node, and we will have as our data item, whatever we want to call it. So let's call it data, which will be of type t, and then the next node in the sequence, node of type t, pointer, which we could call something like next. So this is the variant that you'll see the most often. From that, we can build a linked list of type t. And then to keep track of it, you can do it manually, like the textbook does at the beginning, where you just have a raw pointer to the beginning of the linked list, right? Which you would then allocate a node for, new node, and set its values and all of that. So let's say it was going to store the value 1. You could then have head and data equals, okay, we didn't actually specify a type for it, so let's just make it, let's say, char. The data in that case we can set to be A then. And the next, there is no next at the moment because the head stores, because the head is also the tail, so we will point it to null. So on, and then if we were to have a tail as well, it would point to head as well. Typically, you won't be mucking around in main or something with just these pointers to nodes and then doing everything manually. Typically, what you'll want to do is you want to group everything into a data structure that handles enforcing the rules for you to keep the linked lists correctly organized, and then have member functions for things like inserting and removing and searching and so on. That reminds me, removing from a linked list, which we will look at in more detail, is super efficient. So unlike in an array, if you wanted to shrink an array, there isn't actually a way to do that. You can't just say array be smaller. All you can do is create a new array that is smaller, copy everything except for the thing you want to leave out from the old array to the new array, and then delete the original array and adjust the pointers. So it's not efficient to shrink arrays. Some programming languages have single keywords that do it, like redim in .NET, but under the hood, it's still doing all of that messy copying and transferring, particularly if you say preserve, because then it will make sure to keep the values. So linked lists are super efficient at removals if you've got a pointer to the thing. So removals from the head and the tail are always super efficient with a linked list. So this is just me. So in this case, I've called it info rather than data and link, but basically just similar to what I was doing. Manually created a linked list. Head points to the first node. These are all linked to each other, and then the final link is null to show that that is the tail. There's no explicit tail here, so you could always find the tail by starting at the head, following the links until you hit null, or keep track of it while you go along with a separate pointer. So this idea of moving through a linked list using a current pointer is very important. It's the one that's sort of at the heart of most of the linked list operations. We call it a traversal. And the basic idea is that we can move from one node to another in a linked list by having a pointer to a node and then setting it equal to its own link, which will eventually hit null. So we can test if we've reached the end of the linked list by repeatedly following the links and then checking to see if we've reached null. So for example, we could do that. We had a linked list and we wanted to print it out, say. I'll do it just as separate functions at the moment, but as I say, you'll usually wrap them up in a linked in a data structure. So let's say we're taking a node of type t, pointer, call it the head, And then we would like to print the contents of that linked list. So we will say node of type T pointer, call it current, is equal to the head. And then very importantly, as long as we haven't reached the end, so as long as current is not equal to null pointer, we can then output the stuff, assuming that T supports being output. This would need to be a templated function, just for what it's worth. Template. Okay, and then we could say cout current, and then whatever we called it, data info, doesn't matter. And then we must reverse to the next node. So current is equal to its own. If I call it mine, I think I called it next. That will move us to the next node in the sequence. Eventually, we'll hit the tail, whose next is current. That'll break the loop. And then this is the core idea for whatever it is that you want to do in a traversal. You would just substitute printing out the value with whatever it might be. So traversals are an incredibly important operation in a linked list. Okay, so you took a look at some of the basic ones we said. So traversal, searching for an item, inserting item, deleting item. The inserts and deletes will often assume that you've already got a pointer to the item that needs to be removed or the place after which you want to insert something. You obviously need to find those using a traversal. So traversal is still the heart of all linked list operations. Searching as well, if we could easily turn what we had over here into a search operation, simply modifying the traversal to instead, let's say, and then we're searching for a call it what we're looking for, and then say bool find, and then we will say if t find is equal to current data, turn true, and then at the end, if we didn't find it, we can simply return false. So you can see how the traversal is the heart operation. I'm just going to go and see if there's any questions. Doesn't look like it, so it seems that you're following. Searching and then inserting and deleting. These can get a little awkward, inserting and deleting, when you have to deal with special cases like what do we do if we have an empty list or a list with only one thing in it. There's some extra cleanup that needs to be done in those cases, but in general the ideas are fairly simple. So here we see our traversal, the core operation. This can be modified to do whatever it is you need to do. We saw the definition of the node. I just extended it to be templated, and some basic insertions. So let's just remind ourselves, what's the key operation here? To insert a new node, we basically need to make the predecessor node link to us, and we must link to the previous predecessor's successor. So in this case, 45 is the predecessor, 65 will be our successor. So we need to make the node that contains 45 link to us, and we must link to 65. But we have to do it in the right order so we don't lose the link to 65. If we accidentally, let's say, made 45 point to P first, or wherever, or whatever it is we were putting in, then we will have a problem because we won't have that pointer anymore. So we need to always make sure to either back up those pointers into a temporary variable or do the order of operations in the correct sequence such that we don't lose any information. So in this case, they make sure that they save P's link into the new node, and update new nodes P's link to be new node. So it's easier to see in sequence like this. So create the new node, so it exists there. It doesn't have any data in it yet. Put the data in it. That's fine. Then we need to adjust the linkages. So we make it point to the new successor for us before we update the successor of 65, our predecessor. Then we update our 65 to be our new node's predecessor, joining it into the sequence. So just very carefully remember to yourselves not to lose the data. You very often will be asked questions like this in exams where you have to draw the sequence of events as a diagram relating to some code snippets you get. Or conversely, you could be given some diagrams and say what the code would need to be in order to match that. All right, so we can use 2 pointers to simplify the insertion code. So if you wanted to, you could always keep track of the predecessor and new successor already, and then you can very easily back the code up. That makes it less likely that you're going to make a mistake because you've got a temporary variable storing the pointer that you're in danger of losing. Losing a pointer in a linked list is a disaster because everything after that point is now unreachable to you, because you can only get there, let's say if it's a singly linked list, from the head. So it effectively becomes a memory leak, which is a serious problem, and the data itself is unreachable. You won't know where in memory it is. It could be anywhere. So it's very important to keep the linkages updated correctly and carefully. So here's just doing it with the backup pointer. Here we're safe because we've got in as a local variable our pointed to Q, or pointed to our new successor saved and backed up. So we can safely update our predecessor to point to us because we've got a local variable storing the rest of the array. And then we can safely update us to point to Q, which then links it in, and we're good to go. Deletion is similar. We simply must make sure to first make the predecessor link to the successor of the node, and then we can safely delete the node. This, of course, assumes that this is a non-empty linked list, or a linked list with more than one node in it, so that you have to be very careful about handling the special cases where the linked list only contains a single node, as well as empty linked lists and so on. So we just need to do that. Also remember that unlinking the node from the rest of the list will take it out of the list logically, in the sense it won't show up in any operations, its values won't contribute to anything. So logically it's gone, but the memory is still used up until you delete it. So if you forget to delete the linked list, but remember to unlink it, oh sorry, not the linked list, the node, but remember to unlink it, it'll look like it's working, but if it's a long running program, you'll eventually run out of memory and it'll crash. So do remember to do that. Also remember, it's not an array, it's a node, a single structure, so we don't use the square brackets to delete it. It's a single value that gets deleted. All right, deleting node from the linked list. So yeah, this is basically showing the same thing with two pointers here. So we've got a pointer to the predecessor, a pointer to the node to be deleted, link the predecessor to the node to be deleted successor, so basically link over it, and then delete the node to be deleted safely once everything is correctly routed and linked around. So when we assemble a linked list, we can do it in two ways, forward or backward. This ties into the section that's coming next in terms of stacks and queues, and the basic idea being, if we always add a value to the end of a linked list, we're going to preserve the order of those values. So basically, this is if we've got a bunch of individual variables and want to turn it into a linked list representation. If we continuously add to the end of the linked list, we will be safe. So let's say we wanted to add in the values 1, 2, 3, 4, 5 into our linked list. We start off, we've got the head. So the head will point to, let's say, 1. And then we need to add to this linked list. So we add to the end of the linked list, we add after 1. So then we've got 2. And if we want to add after that, we've got 3. So you can see that continuously adding to the tail of the linked list will preserve the order. If we were always adding to the beginning of the linked list, that wouldn't be the case. We'd start off with h linked to 1, and now we add to the beginning of the linked list. So fine, we add 2, which now links to 1, and then 3, which now links to 2, which now links to 1, and so on. So the order of insertions is important. The location of the insertions is important. If the data is meant to be sorted or not. You can have data where it doesn't really matter the order of the values as long as the values are all there. So what you can see is one way to construct a linked list based hierarchy is to have different subclasses for sorted and unsorted linked lists, where you'll preserve the order in a sorted one, but you don't have to in an unsorted one. So those are definite possibilities. So building a linked list out of a bunch of data, you can do it using 3 pointers. First one to the first node in the linked list, which is the head, and that's not going to be moved. One pointing to the last node, the tail, and then a temporary one that just holds the new node as it's being linked in. First and last, head and tail. Initially linked list is empty, so they both point to null. Then we create a new node and add it in. So first, last, and the new node temporary pointer will all point to this new node. Then we want to create a new node 15, so we add that in. New node links to it. It's not linked into our linked list yet. So in order to do that, we must link the head to the new node, or actually more correctly, since we're adding at the end continuously, we will link what's pointing to last successor to be our new node. So for the first one, they're the same, but from that point onwards, you'll always be using last. So may as well stick to it and not have a special case for the first insertion. So there we go. We update last's successor to be the new node, and then we update the pointer last itself to point to the new node, pushing it across. And you can keep doing that, and you see you've preserved the order, and at the end of the day, you've got last and new node both pointing to the tail. New node you probably won't keep, but last you may well keep, because then you've got a direct link to the end of the linked list. You could do this without the last keyword. It would be super inefficient because you'd have to start at first and then loop through the entire linked list until you hit the one that had null as its successor and re-find it at each step, which would be very inefficient. So it makes sense very often to keep a pointer to last, even if your linked list is singly linked and you can only go forward through it. So you can tweak that for an algorithm to build the linked list backwards by initializing first to null, and then for each item in the list, creating the new node, storing the data, inserting it before first, and updating the value of the pointer to first. We typically will probably do insertion at the end more often because it costs us nothing to preserve the existing order and basically to make our data structure stable. Even if it's an unordered linked list, then it doesn't matter. There's no real cost to preserving the order. So we may as well do it. All right, so you can, all of these operations that you might do with the linked list, traversing it, searching for it, searching it, deleting, inserting, constructing from a set of individual values. There's things that you'll want to do regularly, and you'll want them to follow the rules of being a linked list. So it really makes sense to group all of the data related to being a linked list, which will basically be the pointer to the first node in the linked list and the pointer optionally to the last node as well at bare minimum. All the rest of the data stored in the nodes with the operations that are legal on it. So basically to create an abstract data type for a linked list. Remember, an abstract data type is a data type where the implementation details are kept separate from the logical properties. And that's what we want, because we want our linked list to be, maybe we do later on add in a tail to pointer to the tail to make it more efficient. That shouldn't break anyone's code. It would do that if you just had a bunch of functions taking pointers, because you'd have to add the tail parameter to all of the functions, and basically that would change your API, your application programming interface for your library, which would offend everyone. Whereas wrap everything up in an abstract data type class, you can easily add that pointer, nothing will change because you've created this nice interface to the data. So you'll basically group all of the operations that are legal on linked lists into that abstract data type, such as initialization, test for whether the linked list is empty. There's a couple of ways you can do that. You can have a size variable, a data member that you keep private, and simply return that, and you increment it on every insertion and decrement it on every removal. and then you can simply check to see if that's equal to 0. Alternatively, you don't have to keep track of the size as a variable. You can tell if a linked list is empty if the head is pointing to null. Then it's an empty linked list. So that test is easy to do. But you pretty much often want to find the size of the list. So if you didn't have a size data member in your linked list data type, you would then again have to start at the head, loop until you reach the tail, and count every time you traverse. Which would be inefficient. So it's a very small cost to add a single integer to your linked list data type, and it saves you a lot of trouble later. So may as well do it. Printing the linked list, you can and we will definitely do it. Implement linked lists that have overloaded operators. So for example, you could overload a stream operator to rather just send the contents of the linked list to a stream, which could be output for printing, or it could be a file, or whatever you want. So that's one thing we'll definitely do. Destroying the list, obviously you'll have a destructor, and maybe you might also have a private member function for deleting the linked list, particularly since you will need a copy constructor almost certainly for a linked list. Retrieving the value stored in the first and last element. Why the first and last element specifically is because you'll see those are often the most important elements in a linked list if you're using it to implement another data structure like a stack or a queue. So it does sometimes make sense to have special member functions that will get you the first element and last element's value, not the node itself, just the information stored there. Searching for a particular item, adding an item within the list, removing, duplicating, all things that you generally want to do. So a common approach for linked lists is to split them on the basis of whether you need to keep them sorted or unsorted. The reason why you would do that is some of the operations can be done more cheaply in terms of compute time if the linked list doesn't have to preserve its sortedness. So for those, an unsorted linked list makes sense because you add values cheaply and it doesn't matter whether they stay sorted. So for example, with a sorted linked list, you wouldn't be able to allow arbitrary insertions. You'd have to redirect any arbitrary insertion to be an insertion to the correct place. So an insert at the head would actually first have to run a traversal to find the correct position, which might be the head, but if not, would basically override the behavior so that it would place at the correct location. Whereas you wouldn't need that for an unsorted list. So it would make sense in that sense to have an abstract base class to make it for the linked list itself, and then derive classes for the sorted and unsorted, the ordered or unordered, sorted or unsorted versions. So for an unordered linked list, as I said, this is the big difference. You can insert new items at either the end or the beginning, or arbitrarily in the middle if you add up member functions for it. We took a look at building the lists forward and backwards. And then it makes sense for an abstract, for an unordered linked list to have insert first and insert last. If you put them in the base linked list type, as I said, you'll have to redirect them, or you only add them in the unordered type so that they're not available in general for other linked lists. For efficiency's sake, point to the beginning and end of the linked list, the head and the tail, first and the last. Makes a lot of sense. And we're doing a singly linked list. That'll be our default most of the time. We'll take a look at variants on the linked lists where you can go in both directions. It's called doubly linked lists, as well as linked lists that wrap around, which we call circular linked lists. But the most common one is a singly linked list. And even in practice, in programming languages themselves, they typically will default to singly linked lists. It's doubly linked lists are actually more unusual than you'd think in practice. So anyway, so here's the templated version. Note we tend to use the type name specifier for our type parameters, but other than that, it's the same. So it's what I showed you earlier. And as our data members, we keep track of the size of the linked list with an integer, and then pointers to the head and the tail, first and last, which are node types of or whatever type we specify, so of our type parameter. So yeah, so we will build a singly linked list with overloaded operators, templated, um, uh, as practice for this. You will get one practical related to linked lists. That'll be practical 9, and then you will get asked linked lists in the exam. So they definitely, please note, none of this will show up in the semester tests too. That only covers the stuff we said before. This stuff is for the exam. Let's just see if we have time to do a little bit more. I think I can get the basic idea of this out, or let's just see if there are any questions to deal with. Okay, let's deal with the questions then. Is reverse traversal possible? It is if you've got a doubly linked list. So each node will have a prev and last, or successor, predecessor pointer, and then you can go backwards and forwards all you want. And it works well. Surprisingly uncommon in practice, but it is definitely doable. We will take a look at it. If then, is there a memory leak? Is it possible to get the info back? I mean, let's say no, because you've lost the pointer. In practice, nothing is irrecoverably lost as long as you haven't turned the power off. So you could dump the memory to the hard disk, and then, like if you had like a magic number or something in your linked list data structured data type that you could look for, you could see where in memory it was and update the pointer manually through pointer arithmetic and then recover it. So, technically it's not impossible. You just have to loop through all of your available memory looking for some pattern that you could tell that was part of your linked list. So whenever you're doing memory dumps, it's common to put special values, special numbers that have patterns in hexadecimal that are easy to see. So numbers that when you do a core dump, they call it. Let's say use the number like dead beef or whatever, because it's easy to spot. So then you would know where in memory you, the clever human, would. Or you could write software to search for this. It's possible to get confused because by pure chance there could be this bit pattern in memory that's got nothing to do with your stuff, and then you haven't found it and you're getting corrupted data rather than the right data. So nothing's guaranteed. But so in general, no, there's no guaranteed way in general. In practice, you can try, but it's really, really not easy. So we'll just say no. We'll say it gets lost forever. Yeah, top 7 practicals. Then so the question was how many practicals are taken into consideration. It's the top 7 practicals, including the VPL one. So if you've missed any practicals, or if you've messed any practicals up, or if you're just unhappy with some of your practical marks, do the VPL exercises and fix your marks. That's why they're there. Are nodes similar to 1D arrays? Yes and no, in the sense that they contain a sequential series of values. They're similar, and in the sense that you always keep a pointer to the first one. The big difference is they're non-contiguous. You can't use pointer arithmetic to move from one element to another. So with an array, I could do this. So let's say I've got int pointer a, make it a fixed length one rather than muck about unnecessarily with complex things. So 1, 2, 3. So I could do this in pointer AP is equal to A. That'll get the address of A, or if I felt like spelling it out, I could say that. Doesn't really matter. And then I could do, let's say we've got 0 as a special value that says we're at the end of the list, or a negative value that says we're at the end of the sequence. It's called a sentinel value. So we could do this. So while dereference AP is not equal to our special value, cout star AP with a space, and then AP++. Now this will move the pointer 1 forward in memory, which is fine because they all sit next to each other in memory, so it'll move it forward 1 unit, basically 1 size off chunk of integer forward, and it will always work. But you can't do that with a linked list because they're not guaranteed to sit next to each other in memory. But people love doing this in C++. Using pointer arithmetic to move arrays is a well-established tradition, even though I don't advise it because it causes unnecessary errors and confusion, but it's very common. So that segues nicely into this section here. People, particularly C++ programmers, love to use pointers to access the elements in their collections. But you can't do that with a node pointer in your linked list with pointer arithmetic because of the reasons I said, non-contiguous. So could we create a special kind of class that feels like a pointer and lets you do pointer arithmetic and pointer operations like the dereference operator, but works with the linked list? So basically it allows you to pretend that your linked list is an array. And the answer is yes, they're called iterators. So an iterator is any class that gives you sequential access to the elements in the collection, but the style in C++ is to make them feel like pointers. So they technically count as something known as a smart pointer, because they're classes that implement pointer functionality. For what it's worth, in C++, there are smart pointers to make your lives easier for things like managing memory that will automatically delete the thing it points to when nothing else is pointing to it. Things like shared pointer and unique pointer, and the lesser used cousin of shared pointer, weak pointer, which don't really worry about. We'll take a look at those out of fun because you've now got enough of the skills to do it. But because we force you in semester test 2 to manage the memory manually, you'll use raw pointers with new and delete for your destructors and so on. So but it is good to know about them. So there's another kind of smart pointer. So iterators are a smart pointer. They let you treat your non-pointer or non-contiguous collection as if it were contiguous, like you were using an array. And then smart pointers like shared pointer, unique pointer, to manage your memory for you rather than remembering to delete stuff. So we will talk about those as an extra. So good notice. File handling during the tutorials. Ask a person in your tutorial to do it, but every tutorial is a past paper, and every past paper includes file handling. So the answer is yes, there will be file handling stuff because it's a past paper. So yes, absolutely. Are linked lists and files related? Not at all. You can, of course, save the contents of a linked list to a file or read the contents into a linked list from a file, but they're completely separate concepts. Is Prac 5 included? Yes. If it is one of your top 5 practicals, which basically means if you bothered to do it, it will be in your top 7 practicals. It will be included in. If you didn't upload where we told you to, or you didn't name your thing properly, i.e. after your student number, or if it didn't contain anything meaningful, then you throw away a chance at easy marks, and that's your own fault. But yes, we will include it if you did it. Yeah, I don't know why they're because it does allow for reversal and for forward and backwards traversal. In iterators, you'll see we will implement the plus operators for singly linked lists, and then the doubly linked list you can also implement the minus operator. I agree, doubly linked lists make a lot of sense, but I promise you, when you start to do a lot of programming in languages that use linked lists a lot, you'll see that under the hood they tend to be singly linked lists. It's weird, but that's been my experience. When will we be notified of venues? So we just confirmed the venue sizes today after they adjusted the lockdown level. And so now that we know that, and now that everyone's applied for the things, it'll be today. So just keep checking today, and at some point today there'll be a new mark field on Eve telling you your session and venue. So we just got the confirmation before class started. So now we need to do the allocation, but it'll be up today. And then I think that's it. So I'll actually leave this for Mr. Satunga to start with on. No, it's me tomorrow. I'll carry on with iterators tomorrow. And remember the semester tests on Friday. Remember that we're doing revision in the tutorials. The proper memo for the practical 8 will come out tomorrow, unfortunately, because we were told to give uploaders who failed to upload an extension. That's what happens. I don't really know how useful the prac is then from a prac point of view, because it's sort of spread out like that, with some people submitting early and some people not. So we'll talk about how we'll handle that from a calculation point of view. It does. It's and a lot of almost religious preferences. So you'll go from one programming house where they hate tabs and love spaces to another one where it's the reverse. Or in C++, you can program things in a lot of different styles. C++ supports a wide variety of things, so different subsets will be used. I can't extend the test date. That's set by the Faculty Higher Degrees Committee. In fact, it's set by the University Timetables Committee. I don't have the authority to move a test date. I can. The best I can do is if we have to set a special supplementary test for things, as I might have some say in choosing the date for that. But even then, sometimes I don't. We don't set the test dates. That's set at a much higher level. Same for exams. We don't have control over that. They tell us. So yeah, but remember, for the test, just do what's on the mark fields. The mark fields at the back tells you where the marks come from. If you don't quite understand the question right and you mess it up a little, you'll lose some marks. Like if you look at the last year's paper, there were 5 marks for the algorithm for doing the visualization of the Martian surface. But if you do everything else right, if you have the composition correct, if you have the inheritance correct, if you have the polymorphism correct, even if your algorithms are wrong, you still get the marks for doing the right thing from a data structure architecture point of view. So you can rack up the marks by doing those things correctly, even if you make a mistake in understanding the core question, right? Don't do something stupid like upload a UJ image and say, oops, I misunderstood the question and this has got nothing to do with images, because then you'll just fail. But if you made a genuine effort to try and understand it, even if you got it slightly wrong, but you did the stuff correctly, like you handled the files correctly, you did composition, delegation, inheritance, polymorphism correctly, you get the marks for doing those things correctly, even if you made a mistake in your understanding the question story itself. So yeah, as long as you made a genuine attempt, that's fine. Yeah, so there you go. Your marks are for the process, but please test it and make sure it compiles. That's very important for the test, because it still gets capped. It's not the rules aren't that it gets capped at 40. The rules are that it gets capped at a fail. So I try and get away with capping it as high a fail as I'm allowed to, but it has to still be maximum 49%. So please bear that in mind. Why load from file stream using ifstream? Because they've got the stream stuff built into them. So you'll use fstream if you need to move manually byte by byte using seekp and get, seek and get and things like that. Whereas with the ifstream and ofstream, they've got the proper sequential stream operators implemented. So that tends to be why you do it. And also you're signaling intent with it, because you're signaling that this is a sequential file that you're working with. So that's the reasons for it. Oh, well, for ifstream is input, ofstream is output. That one's easy. But if you're asking why you use them instead of fstream, fstream you'll use files of records and other binary files where you need to move to exact byte positions, rather than worrying about a sequence of values. Okay, so those were really great questions, but we're quite a bit over time now. So I'm going to stop this session. Have a great afternoon. See you in class tomorrow. Mr. Satunga will see you this afternoon in the tutorial. All right, stopping recording.